It is summary of lecture 28 on similar matrices. Let's begin by the definition of what similar means, and I will begin by the definition in the lecture and the one in the book. Let's begin by the one in the book. So it all comes from this diagonalization. So remember that S is our eigenvector matrix, and our this capital lambda is our eigenvalues matrix. And then remember, you can put the S into the right hand side, then you have S inverse here. Then this statement alone, actually this will also be what I'm going to tell you in this point. So this statement alone, this is enough to say that our A and our capital lambda here is similar. So that's the new term that we are introduced in this lecture. This thing are similar. Okay. Now the first paragraph in the book mentioned that actually you don't need to have you don't need to use this eigenvector matrices. You can also use any kind of arbitrary matrix. Let me put a letter M there. In the book I believe it was B, but I'm just going to use the M here so that you can have a comparison with what the Professor Shrang introduced in the lecture. You can have any arbitrary vector here, arbitrary invertible matrix, as long as it's an invertible. Okay. And then also you don't need to have the diagonal matrix of lambda here. You can pick also any kind of matrix here, B. And if this multiplication equals to A, then this also says that the A and B, these two things are similar. Okay. And notice I forgot the inverse here. Okay. And from here, actually, you got the definition that is introduced initially in the lecture, which is if you just put B on the left hand side and then you put M on the A side here, then you have the M inverse AM. Okay. Now I just want to have it here written here, like, let me try to read right here again. So A, M, B, M inverse. So notice that the M inverse location is different, but they're telling you the same thing, so the point stands. They're both correct. In fact, it is just another way of saying that B is similar to A, or this A is similar to B, which are really interchangeable, right? So first, that's what I want to point out here. The definition of A and B are similar is either this and this. And let's stick with this one. Okay, let's stick with the one in the lecture first. Let me put a square there. Okay, so B is similar to A. If you start with A, okay, you start with A, you have some matrix here, and then you have any arbitrary matrix M and M inverse, and then you multiply them, you got a new B. And you say that B and A are similar, right? Cool. So that's my first point. We done. And then another thing is that we no longer expecting symmetric matrices here. So just a side note that we don't need A or B to be symmetric any longer. That it can be any matrix here in this discussion. Okay. And then my third point here, which also relates to this equation, is that the lambda here is like I really like the word the outstanding member in this family. So right now, if I write like this, then A, B, and lambda are similar. They belong to some family. They are a family because why? Because they have the same eigenvalue, which is what I'm going to prove next here. But just remember that the first requirement, or the first characteristic of being in a same family of being similar is that they have the same eigenvalue, but this alone is not enough. So I will tell you more about that in part 2 when we talk about the bad case and the Jordan form. But first, one of the requirement of being in a similar matrix is they have the same eigenvalues, right? So let's run an example. So let's say I have this A is 2, 1, 1, 2. Just happen we have a symmetric matrix here, but remember it doesn't have to be symmetric, okay? And then from here, the lambda is 3, 0, 0, 1. So the lambda, the eigenvalues of A here is 3 and 1. It has 2 eigenvalues. This is actually just an example in the class. And here let's just invent matrix M, right? Matrix M to be 1, 4, 0, 1, and then the inverse of that is the 1 minus 4, 0, 1. And then if you do this multiplication of M inverse AM, then you will end up with a matrix B, which are minus 2, minus 15, 1, 6. And a quick check of the eigenvalues of B is that the eigenvalue 1 times 2 is the minus 12 plus 15, which is 3. Okay, and then the trace, like the eigenvalues, the sum of eigenvalues is 4. So this is also the same thing. We start with the eigenvalues of 3 and 1. The sum of them is 4, and the product of them is 3. So this matrix and the A and our lambda are similar. They are all similar. Okay, good. So let me delete some of this, and then I want to prove to you the eigenvalues of being equal. Let's continue on with proving the eigenvalues of being equal. And this proof is also will state that what happened to the eigenvector. Let's start right away. Let's start with the definition in the lecture, right? So we have the B is similar to A, given if B is M inverse AM, and then let's start with the known facts that we have the A times the eigenvalue is equal to the eigenvalue times the eigenvector. A times the eigenvector times the eigenvalue times the eigenvector. I'm sorry about that. Okay. And now let's put the M inverse here, X, and that's just the identity, which does nothing to the right hand side. And then I will multiply both with the M inverse. Okay, here goes M inverse, and then lambda is just a constant, so it can be pulled out this way. And then this thing right here is just my B. So I have the M inverse X there. So let's see here what we have. So what can be proven here is that, see that the eigenvalue lambda is still the same of A and B. What changes is that the direction of the eigenvector. You see the initial eigenvector A that is X now is the M inverse X in terms of B, right? So that's one thing. And then I just want to again compare it with this one, the definition in the book, because there's also an example in the book that also touches this discussion right here. So let's start with this definition. Now I have initially I have B eigenvector is the eigenvalue and eigenvector, right? And then similarly, somehow I'm trying to achieve this form, so I need this M inverse M X, which is just the identity, and you can just notice that these two are the same, M inverse M, they are the identity, it doesn't matter. And then you can put the M here, right? And then this one is just the A that we have, and then mx, and then you have the actually M here, and then lambda mx. Now if I put brackets there, then you can see now again the lambda of b initially, that if we're starting with b, then it will be the same lambda with a, and then again the eigenvector changes direction. And see that, you know, why these two are different, the mx and m inverse x. Again, it's just a different starting point of where you start with. How do you start? I believe the book it has this definition of here, that it in the example or in the proof they said that the eigenvector change direction of mx, while in the lecture professors mentioned about the eigenvector change to m inverse x. So let's just realize that these two are telling you the same thing. Now let's move on with a not so good example, the bad case of similar matrix. See you in the part 2.